Chapter 18, Rotational and Vibrational Transitions of Molecules. Section 18.4, Non-rigid rotors and anharmonic oscillators. Real diatomic molecules are non-rigid rotors and anharmonic oscillators. The non-rigid rotational energy levels are J times J plus 1 times Hc B sub E minus J squared J plus 1 squared HCD when the centrifugal distortion is considered. B sub E is the rotational constant at equilibrium bond distance. J is the rotational quantum number, and D is the non-rigidity constant. The value of D is much smaller than B sub E. Therefore, this term J squared J plus 1 squared HCD is usually much smaller than J times J plus 1 times HCBE, unless J is very large. So usually when J is smaller than 10, the first term is much larger than the second term. The anharmonic vibrational energy levels are n plus 1 half Hc omega E minus n plus half squared Hc omega E chi E. Omega E is the harmonic oscillation wave number at equilibrium bond distance. K sub E is uniless. K sub E is the anharmonicity constant. This is chi. Chi sub E is usually between 0.01 and 0.05. It's much smaller than 1. Therefore, this second term is usually much smaller than the first term here, unless n is large. Now we have the rotational energy for a non-rigid rotor. We have the vibrational energy of an anharmonic oscillator. There's another term. The vibration and rotation of a real molecule are coupled. There's a so-called rotational vibrational coupling energy. So we have this term negative n plus 1 half times J plus 1 times Hc alpha E, and alpha E is the rotational vibrational coupling constant. Well, why do rotation and vibration couple? Here's one example. When a molecule vibrates rigorously, on average it has a slightly longer bond distance, and that will change the rotational energy spacing, and of course it's going to change the rotational constant. So that's why rotation and vibration are coupled for a real molecule. And over here, this correction is a native correction, and we have all 5 terms written over here as the sum of the rotational and vibrational energies of a real molecule. Now let me explain all those 5 terms one more time. Here, n plus 1 half times Hc omega E, that's the harmonic vibrational energy. Now we have this correction, anharmonic correction, negative n plus half squared Hc omega E chi E. Chi E is a very small number, between 0.01 and 0.05 for most molecules. J times J plus 1 times Hc B sub E is the rotational energy of a rigid rotor. Now we have this centrifugal distortion term, negative J squared times J plus 1 squared times HCD, and D is much smaller than B sub E. So as long as J is not too large, this term is smaller than HCB term. Finally, the rotation and vibration are coupled for a real molecule, and we have the coupling here minus n plus 1 half, that's from the vibration, J times J plus 1 from rotation, times H times C times alpha E. Alpha E is the rotational vibrational coupling constant. So over here, omega E, B sub E, D, and alpha E, those are wave numbers. The SI unit is meter to the power of -1, but commonly we use centimeter to the power of -1 for omega E, B E, D, and alpha E for historical reasons. Again, the sum of the rotational and vibrational energies of a real molecule, a real diatomic molecule, is this. We have the harmonic vibrational energy, we have the anharmonic correction, we have the rotational energy of a rigid rotor, we have the non-rigid correction, and finally we have the rotational vibrational coupling. Now, when a molecule undergoes a 0 to 1 vibrational transition and J to J plus 1 rotational excitation, we can predict the wave number of the absorbed infrared photon. It's very easy. The energy of the photon should be the energy difference between the initial and final state. In the initial state, the vibrational quantum number is 0, the rotational quantum number is J. In the final state, the vibrational quantum number is 1, the rotational quantum number is J plus 1. Now we have this equation. This is the energy difference between the initial and final states. Divided by Hc, we have this equation. We have over here, this is the final state, this is the initial state. So we have the final state minus the initial state over here. The final state, we have a n equals 1 vibrational quantum number. So over here, n equals 1, n equals 1. This is harmonic vibrational energy and harmonic correction. Also, let's look at the rotational energy when J plus 1 is the rotational quantum number. So over here, we have J plus 1 times J plus 2 BE minus the non-rigid correction. And right here, we have the coupling between vibration and rotation. For vibration, the quantum number is 1, so we have 1 plus 1/2 here. And then for the rotation, the quantum number is J plus 1, so we have J plus 1 times J plus 2 over here. And again, omega E, BE, D, and alpha E, those are wave numbers. Chi E is unitless. Now let's look at the initial state. In the initial state, the vibrational quantum number is 0, so we have just 1/2 omega E minus 1/4 omega E chi E. And over here, this is the initial state J, so we plug in J here. And this is the non-rigid correction when the rotational quantum number is J. And over here, we have the coupling. The vibrational quantum number is 0, so we have n plus 1/2 equals 1/2, and then J times J plus 1, and then times alpha E. This is really tedious. We see 1, 2, 3, 4, 5 terms for the final state, 5 terms for the initial state, and we need to take the difference. After we take the difference, we have omega E minus 2 omega E chi E plus 2 times J plus 1 times BE minus 4 times J plus 1 cubed times D minus J plus 1 times J plus 3 alpha E. So this is going to be the wave number of an IR photon absorbed by a real molecule when this molecule undergoes 0 to 1 vibrational transition and also J to J plus 1 rotational excitation. So by looking at this, we know it's going to be the R branch. All right, the value of the rotational quantum number increases. So this is the R branch. We have 5 terms here. Again, this term comes from the harmonic vibration, anharmonic correction, rigid rotation, non-rigid correction. This comes from the vibrational rotational coupling. What molecule undergoes 0 to 1 vibrational transition and also J to J plus 1 rotational transition? We have this formula as the wave number of the photon absorbed by this molecule. Given a high resolution set of data of the infrared wave numbers versus J, we can simply plot this delta E over Hc versus j and determine the value of the parameter d for the centrifugal distortion by fitting the infrared data with a third order polynomial function of j. So you can see on the right hand side we have a third order polynomial function of this quantum number j. Delta E over hc is just the wave number of the photon that we can collect from the infrared spectrum. The coefficient in front of the j cubed term is negative 4d. You can see from here it's negative 4d times j to the power of 3. Of course, there are other terms like j squared and j to the power of 1, etc. But if we just focus on fitting the data to a third order polynomial function of j, the coefficient in front of the j cubed term is negative 4d, and we can compute d. The value of d is much smaller than b sub e. When j is not very large, we can neglect this non-rigid correction or centrifugal distortion. So over here, 2 times j plus 1 times b is much larger than 4 times j plus 1 cubed d. So when that's the case, well, we can simplify this equation, and on the right hand side you will see a second order polynomial function of j, also called a quadratic function of j. So this is the simplified equation when we can neglect the centrifugal distortion or so-called non-rigid correction to the rotational energy. And again, this is a second order polynomial function, so it's a little simpler, and somehow we can plot the wave number here. This is the wave number of the infrared photon versus j. We can get a Excel graph, and we can fit the data with a quadratic equation and then determine some of those values, for example this value and b value, alpha e value, etc. Alright, when j is not very large, we can neglect the centrifugal distortion or so-called non-rigid correction to the rotational energy, and the R branch peak wave numbers are expressed as a second order polynomial function of j or a quadratic function of j. We can just expand everything over here. This is just j plus 1 times j plus 3. I think you'll get j squared plus 4j plus 3, and then you just expand everything and you group the j squared term, you group the j term, and you group all the terms that does not contain j at all. And also we realize that omega e minus 2 omega e chi e is simply the wave number for the pure 0 to 1 vibrational transition. So I'm using omega sub 0 to 1 to express this omega e minus 2 omega e chi e. And this way we have a fairly simple quadratic function of j. We have 3 coefficients. In front of j squared, it's negative alpha e. In front of j, it's 2be minus 4 alpha e. And then we have zeroth order term here. The first one is wave number for the pure vibrational transition, and pe is just rotational constant. Alpha e is the coupling between vibration and rotation. And now we can just determine, using a quadratic equation fitting to determine the coefficients in front of j squared, in front of j, and then this term as well. Now let's look at the p branch. In the p branch, the rotational quantum number decreases by 1, so it's going from j to j minus 1. And we're going to do the derivation as well over here. So over here we're going to look at the final state minus the initial state. In the final state, the vibrational quantum number is 1. In the initial state, the vibrational quantum number is 0. So there's a difference here and here. There's a difference here and here. Over here, this is 1.5 squared. This one is just 0.5 squared. Now let's look at rotation. This is rotational de-excitation. The value of j decreases. It goes from j to j minus 1. So over here we have j minus 1 as the quantum number. Therefore, it's j minus 1 times j times BE. And over here, it's just j times j plus 1 plus times BE. Now we have the coupling. When we have the coupling, we need the vibrational quantum number, which is 1 here, 1 plus half. And then the rotational number, which is j minus 1 times j. Here, over here, we have vibrational quantum number 0, so it's just minus half, and then times j plus 1. Again, it's the final state minus the initial state. We can clean up a little. We get omega e minus 2 omega e chi e minus 2j times be, and then minus j squared minus 2j times alpha e. So we again get a quadratic function of j. It's negative alpha e j squared plus 2 alpha e minus 2b times j plus this omega sub 0 to 1. This is the pure vibrational transition wave number. So the values of alpha e over here and be over here and omega 0 to 1 can be determined if you plot the p branch data, that means p branch wave numbers over here, versus the value of j, and you need to do a quadratic equation regression analysis. Alright, and again, I mean, if when you do a quadratic regression analysis, you'll get something like, ax squared plus bx plus c, right? So ax squared, the value of a is the value of negative alpha e. Bx, the value of b is this whole thing. The value of c is this. So we can somehow determine the values of alpha e, be, and omega 0 to 1 given the wave numbers of the p branch waves. Now let's look at the R branch data analysis and P branch data analysis together. For the R branch, the photon wave numbers can be expressed as a quadratic function of j. Same for the P branch, it's a quadratic function of j. Well, these two equations look quite different, except the j squared term, that's the same. But then if you look at the j term, they look different. If you look at this term, they also look quite different. But we can use a mathematical trick to pull the R branch data and P branch data together in the same Excel graph, and then do a quadratic analysis altogether for all the data. The mathematical trick is this: variable substitution. If we somehow set m to be j plus 1 for the R branch, we'll replace this j with m minus 1, this j with m minus 1, and we get this expression. Well, of course, it looks more complicated. We expand everything, but then, well, a lot of terms can cancel, and in the end, we get a quadratic function of m, negative alpha e m squared plus 2 times b minus alpha e times m, and then plus over here, this is the pure vibrational transition from 0 to 1 for a anharmonic oscillator. Now for the P branch, we set m to be negative j. Now it's simple, j is negative m, so we replace this j with negative m, this j with negative m, we just get this quadratic function. Now let's compare the two quadratic functions, one for the R branch, one for the P branch. They are exactly the same, and therefore we can simply plot the wave numbers of the photon, which is delta E over hc, versus m instead of versus j versus m. M, well, is defined to be j plus 1 for the R branch. M is defined to be negative j for the P branch. Now we have only one equation to use for all the data from the P branch and from the R branch. Again, I just want to emphasize that m has a different definition for the R branch and another definition for the P branch. M is j plus 1 for the R branch, m is negative j for the P branch. For the R branch, m can be positive 1, 2, 3, 4, 5. For the P branch, m can be negative 1, negative 2, negative 3, negative 4, negative 5. Can m be 0? No, m cannot be 0, because if m is 0, that means, well, when m is 0, that means there's no rotational excitation or the excitation. That's forbidden. Alright, m has to be either 1, 2, 3, 4, 5, or negative 1, negative 2, negative 3, negative 4. -5, etc. We do not have the data when m equals 0. Or you can just look at this equation, this unified equation. When m is 0, well, we have the wave number equals the pure vibrational transition wave number, and again it's forbidden because you have to have a rotational excitation or de-excitation, and the rotational quantum number must change by 1. Again, we can use this equation, unified equation, for both the R branch and P branch. So we can collect the wave numbers in the R branch and P branch, and then we plot this. Just remember, M has a different definition for the R branch than for the P branch. For the R branch, M is J plus 1. For the P branch, M is -J. The values of alpha sub E, B sub E, and omega sub 0 to 1 can now be determined by plotting the infrared wave numbers versus the value of M, and we can just fit all this data with a quadratic function of M. The value of B can then be used to determine the equilibrium bond distance, R sub E, of this diatomic molecule using this definition of the rotational constant. HCB is defined to be h bar squared over 2I. This B sub E, it stands for the rotational constant when the bond distance is the equilibrium bond distance. And this B sub E, we just usually it's several wave numbers. You know, for HCl, I think it's about 10 wave numbers. For other diatomic molecules, B sub E can be smaller than 10 wave numbers or larger than 10 wave numbers. But anyway, once you have the value of B sub E, you can compute this R sub E given the reduced mass. And not only that, if we have the value of the 0 to 2 overtone vibrational transition wave numbers, that's for the transition from n equals 0 to n equals 2, and this is 2 omega e minus 6 omega chi e. If this value is also available, then we can somehow determine omega e and chi e simultaneously, because we'll be able to get this omega from 0 to 1 using this quadratic fitting. And also, if somehow you obtain a value from 0 to 2, and then we have this value, omega 0 to 1, omega 0 to 2. We simply have two linear equations that contain two variables. One variable is omega e. The other variable, you may consider the other variable to be omega e chi e. So we can determine the value of omega e and then omega e chi e, and then you can determine chi e later. The 0-point vibration energy of an anharmonic oscillator is this. You can do a simple calculation given the formula for the vibration energy of an anharmonic oscillator. It's h times c times 1/2 omega e minus 1/4 omega e chi e. So over here, this comes from n plus 1/2. This is n plus 1/2 squared. The bond energy of a diatomic molecule is the depth of the potential energy well minus the 0-point vibrational energy. So we can solve for a lot of things, but again, you know, the first thing we need to do is we need to have the infrared wave numbers from a high resolution infrared spectrum. Alright, all those wave numbers. We do need to identify R branch and P branch. We need to identify the value of J first for the R branch and for the P branch. For the R branch, it can be 0 to 1 transition, 1 to 2 transition, 2 to 3 transition. So the value of J is 0, 1, 2, etc. And we define M to be J plus 1. So the value of M is 1, 2, 3, etc. And now we look at a P branch. The transitions can be from 1 to 0, 2 to 1, 3 to 2, and then we define M to be -J, and then we can pull all the data together. Both the R branch and the P branch data can be pulled together in the same Excel graph. If we redefine, you know, this variable M to be J plus 1 for the R branch, M is -J for the P branch. Now let's look at one example. It's easier to see a real numerical example to understand the data analysis. Now let's say we collected the high resolution infrared spectrum of this hydrogen chloride, this chlorine 35. The reason I specify 35 is when you have chlorine 37, you have a different reduced mass, and the wave numbers shift a little bit. Now let's look at this. J has to change by 1, so when J becomes J plus 1, it's R branch. When J becomes J minus 1, it's P branch. We collect all those wave numbers. We have the values of J. J is 0, 1 over here. J is 1 and 2 over here. We redefine a new variable M. M is J plus 1 for the R branch. Alright, and M is negative J for the P branch. That's why over here this M is 1 plus 0. This 2 is 1 plus 1. And over here this is just negative 1. This is negative 2. We copy those wave numbers here, but I decided to use the SI unit over here just to remind students that traditionally we use centimeter to the power of negative 1. Sometimes we call that wave numbers, but it's not an SI unit. All those are SI units. So if you really want to do the calculations without worrying about the unit conversion, I would start with the SI units from the beginning, and then every single value you get is in the SI unit. Now we have 4 data points. We have this 4 wave numbers per meter, and we have the value of M. So we plot this graph, the infrared wave number in the unit of 1 over M, and the horizontal axis is the value of M. M is negative J for the P branch, so we have P branch data here. M is J plus 1 for the R branch. M is 1 and 2 over here. You can see the R branch data have higher wave number than the P branch data, only because over here we have rotational excitation, here we have rotational de-excitation. So over here we need a higher frequency photon, here we need a lower frequency photon. The wave number is proportional to the frequency. And now let's look at the data fitting. You have to use a quadratic function over here. So I'm using a quadratic function. I get y equals negative 30x squared plus 2057 plus over here 288,565. R squared is 1. So really we just compare this coefficient in front of M squared with this coefficient in front of X squared. So we can immediately see alpha sub E is 30 per meter. 2BE minus 2 alpha E is 2057 per meter. And this omega from 0 to 1 is 288,000 per meter. Again, the wave number of the absorbed infrared photon for a real molecule can be expressed as a quadratic function of M. M is negative J for the P branch. M is J plus 1 for the R branch. We do a quadratic fitting over here, and then we can solve for alpha E, BE, and omega from 0 to 1. So again, we just compare this two. We see alpha E is 30, 2B minus 2 alpha E is 27, omega 0 to 1 is 280,565. The unit is meter to the power of negative 1. Sorry about using M for meter and M for the variable, but unfortunately in physical chemistry, every single English letter has 5+ different meanings, and so does every single Greek letter, I believe. Now this alpha E is determined, 2B minus 2 alpha E is determined, omega from 0 to 1 is determined. So by looking at these two equations, I think you can easily determine the value of B sub E, which is this. Why do we need this? Well, as long as we have B sub E, remember H times C times B is H bar squared over 2I. So if you have Planck constant times the speed of light times this value, well, the result is equal to H bar squared over 2I. H bar is a constant as well, so you can determine I, the moment of inertia. Given the moment of inertia, you can determine the equilibrium bond distance easily, as long as you know the reduced mass. And it's awfully easy to determine the reduced mass for a diatomic molecule. For example, HCl, you have mass 1 AMU, mass 2, 35 AMU, and then mu is very close to 1 mu. I think it's 1.62 times 10 to the power of negative 27 kilogram ish. And then once you have the reduced mass in the SI unit, you have the moment of inertia determined from the value of the rotational constant B sub E. You can determine the equilibrium bond distance for HCl, and that's experimentally how chemists determine the bond distance for diatomic molecules. And over here we have the wave number for the pure vibrational transition. Given this number, we can determine the difference between the depth of the potential energy well and the bonding energy for a diatomic molecule, which is just 1/2 times H times C times this number.